Last time we were looking at constant velocity motion, and ultimately for constant velocity motion we ended up with this mathematical model. The position, as it depends upon time, is the velocity times the time plus the initial position. And you saw that this was basically the general y equals mx plus b linear form um, of, of an equation. Um, I think you're about to see that we can no longer use this equation if the object is experiencing acceleration, if the motion is changing, if the velocity is changing, if it's speeding up or slowing down. This equation only works for a line, and as you're about to see, for accelerated motion, the position time graph yields a curve with a changing velocity. This equation only has one constant velocity. Constant velocity gives a line, a straight line. This is a linear equation. That's not going to be the case for accelerated motion. So I have two objects here. We're going to look at them one at a time. Let's start with the red object. Just like last time, we're going to start graphing this. This is time 0. This is time 1, time 2, time 3, time 4, and time 5. You remember the time is graphed on the x-axis. The position, which we represent with an x, is graphed on the y-axis. So at time 0, this object is at -10. Okay, so you can see that I've graphed the points for the red object. And you can see, I think, very clearly that this does not make a straight line. It makes a curve. So this is not linear. And that is because for a position time graph for an accelerated object, the data will yield a curve. So I'm going to try to draw this curve here. Now, we have to make several important observations. The first thing that we should notice about this object's motion is that it is slowing down. This object is moving to the right, so the red object has a positive velocity, but it's slowing down. The velocity is decreasing. The dots are getting closer together. My vector lines are getting smaller and smaller. We know this object is slowing down. And then here at 5 seconds, it looks like it stops. Positive velocity, remember that just shows you direction. It's moving to the right in a positive direction. And this graph still shows that. It is increasing its position. As time goes on, the position on the x-axis increases. So the line goes up and to the right. That is what this tells us. A positive velocity is going up and to the right. However, what can we say about the acceleration? The acceleration for this object is negative. It has a negative acceleration. How do I know that? Because it's slowing down. The signs must oppose each other. What I notice about the curve here on the graph is that it is getting shallower and shallower. If you were to right now on your screen hold up a ruler or a straight edge or something like that and kind of trace the curve with your straight edge, you would see that it would start very, very steep here at the beginning. By the time you got around here, it would almost be horizontal. I'm going to represent that real quick by drawing what are known as tangent lines. Tangent lines are lines that touch your main line at only one point. So my tangent line here, this is kind of what I was talking about with the straight edge, would be incredibly, incredibly steep. But then you can see as you go along, your tangent line is getting shallower and shallower. So what does that tell you? Remember, what quantity are we concerned about that deals with the steepness of a line? The velocity. Well, the line is getting shallower and shallower. It started very steep. It ended quite shallow. So this object is slowing down. The velocity is decreasing. You have got to be able to look at a graph like this and know that the velocity is positive. How do we know that the velocity is positive for this red object? Well, because it's going up and to the right. The position is increasing as time goes on. How do we know it's slowing down? Well, because it is getting shallower and shallower. So the acceleration is negative. We could do several things with this. We could find the average velocity. We could find one average velocity for this entire trip. I think you know how to do that using the motion map. I'm going to show you how to find the average velocity using this graph. In order to do that, we draw a line that connects the beginning and the end, and we find the slope of that line. Pretty simple. So instead of taking into consideration all of the changes here, remember acceleration means a change in instantaneous velocity. The velocity is decreasing, decreasing, decreasing. The average does not really care about that. The average is an overall comparison of the starting and the ending. So I would have a line like this. It's supposed to be straight, linear. How do I find the velocity of a straight line on a position time graph? It's delta x over t. What's the overall change in position? Final position was 5, initial position was negative 10. Final minus initial over, how long did that take? It took 5 seconds. That's going to be an average velocity of 3 meters per second. You would have gotten the exact same thing if you did that here. So just by playing a game of connect the dots where we don't worry about what happened in the middle, we're just worried about the overall, that is how you can find the average velocity. But it would be incorrect to say that the velocity of this object is 3 meters per second because of course the velocity is changing, it's slowing down. So I would have to talk about the changing instantaneous velocity. And it's possible for me to find the instantaneous velocity at a point simply by taking the slope of the tangent line at that point. Let's say, for instance, that you are asked to find the velocity when time equals 2 seconds. So you can see I've done my best to draw a tangent line, a line that kind of represents the slope at that point when time is 2. It should hit the line just one time and then keep going. That's the definition of a tangent line. If I find the slope of that tangent line, it should approximate for me, it may not be exact, but it should approximate for me the velocity at 2 seconds. This is true for objects with acceleration, objects whose velocities are changing. The velocity is constantly changing. This line is constantly getting more and more shallow, less and less steep. It's slowing down. So until you take calculus, this little game of playing approximation using tangent lines is really the best way to find the velocity at that point. So I'm just going to find the slope of this line. Hopefully you remember that slope is rise over run. So the slope of that tangent line is going to be the rise. I'm just going to pick some points here that I can see quite easily. Looks like 0, -6, this point right here. So it starts at -6, and it looks like it rises. Let's say I pick this point right here, rises to a 4. That is a change of 10. 10 is my rise. My run, I started at 0, and to get up here to a point of 4, I had to go over, it looks like 1, 2, 3. 10 over 3. That's going to be about 3.33 meters per second. That is kind of my approximated velocity at time equals 2. Let's see if that makes sense up here with the motion map. Between 2 and 3 seconds, it was going at a velocity of 1, 2, 3 meters per second. Before that, it was going at a velocity of 1, 2, 3, 4 meters per second. So yeah, it makes sense that at this exact instant, it's going somewhere in between. So that's a pretty good approximation tool. Drawing a tangent line, a line that hits the point of interest. I was worried about t equals 2 seconds on my main line. Drawing a line that hits that just at one point, and then finding the slope of that. The slope of the tangent line can give you the instantaneous velocity for any moment. So we have shown that we can do several things. We can represent accelerated motion where the velocity is changing with the curve. The velocity, the instantaneous velocity is changing. So we know right away this object is going with a positive velocity because we're moving up and to the right, and it's slowing down. Negative acceleration, positive velocity is slowing down because it's getting more and more shallow. All right. We've seen that we can take the average velocity just by drawing a line here between the beginning and ending points and taking the slope of that. And we've seen that we can find an instantaneous velocity for any given point by drawing tangent lines. Let's compare now the graph that the blue object makes. This blue object is moving with a negative velocity because it's moving to the left. It starts at time 0 at a position of 5. Remember, this is my reference frame. These are my positions. The first second, it has reached the position of 0. It's reached the origin after 1 second. The second second, it has reached the position of -4. Several things to notice about this compared to the red object. The red object is moving up and to the right. That's a positive velocity. The object is moving to the right. This object is going down. And so it's going to have a negative velocity. This slope is negative everywhere. The position is decreasing. The position is going down. The position is decreasing as time goes on. Negative slope. What about the acceleration? What do you think the acceleration is going to be? It's got to have a positive acceleration. How do you know that? Well, think about this. The steepness of the line shows you how fast the object is going, the velocity. Is this blue line getting more steep or less steep? It's getting less steep. It starts out very steep, and then it gets more and more and more shallow. Remember our tangent line trick. We could draw tangent lines here. There's a tangent line. Here's one. Here's one. These tangent lines are getting shallower and shallower. So the velocity must be decreasing. If the velocity is decreasing, if the velocity is becoming less negative, in other words, the size of the velocity, the object is slowing down, then the acceleration must be positive. They must be opposing each other. I hope that makes some good sense for you.